In this video, I wanted to do another example of multiplying matrices and use it as a way of talking about particular properties of multiplication within the matrix, within matrices. So, like in normal numbers, multiplication is what's called distributive, commutative, associative, which has a certain implication. Like the distributive property, the distributive property is one I'm sure you're familiar with from algebra class, is that if we have, say, 3 times x plus 4, um, it will obey the distributive property, meaning that 3 will multiply into each term, 3 times x and 3 times 4, and we'll have a certain particular answer. Which certain properties work amongst the matrices is the same way they do in normal math. And how I like to say it is the algebra is the same, meaning if I was working with matrices, that exact same property holds up. But another property, which we refer to as the commutative property of multiplication, is that if I take 3 times 4, that's obviously 12. It's the same product whether I reverse the order of the numbers, right? 3 times 4 and 4 times 3. It's always equal, and we refer to that as commutativity of the operation of multiplication. Not all operations are commutative. Like, for example, subtraction, right? 7 minus 3 is not the same as 3 minus 7. While technically they're the same absolute value, it is not a commutative operation because the order does matter. Whereas with multiplication, the order does not matter, hence it is commutative. But the reason I bring this up is because within the matrices, matrix multiplication is obviously not commutative. First of all, because the rule about the dimensions. Like I said with the previous example, this matrix multiplication A times B worked because matrix A had 2 elements going into the columns of matrix B had 2 elements. That was all well and good. But let's imagine instead of trying to do A times B, we were looking at the reverse. We solved A times B in the previous video, which was a 2 by 3 matrix. But what if we were considering the opposite order, B times A? What would that look like? Well, notice that if I'm reversing B times A, B would be my first matrix and A would be my second, meaning I would take the first row of B and try to multiply that into the first column of A, because it always goes row of the first into column of the second, by definition of how matrix multiplication must work. But notice that if I try to do B times A, what I get is a dimension mismatch because 3 elements will not multiply into 2 elements, and what I get is something that does not work. So clearly, I can't reverse the order of that multiplication problem. I don't get the same thing. And even if I were able to, like with one of the great values of square matrices is that if I have 2 square matrices of the same dimension, I will always be able to multiply them in either order, right? Because if it's 2 by 2 and 2 by 2, when I multiply them together, I'm going to get another 2 by 2 matrix. So matrices which are square don't have the problem of prior multiplication examples because the dimension doesn't change, which can be awkward depending on the context of what we're using the matrices for. But even when they are square matrices and we try to multiply them, it still doesn't necessarily give us the same answer when I switch the order. So in this example, let's figure out what is AB and BA and kind of compare to just look at what we get. So if we try to do matrix A, if we try to do matrix A times matrix B, let's just copy them down right here, 5, 7, negative 3, 0. And 1, 2, 9, negative 1, this would be A times B. And again, running through the usual set of inner products, I would get 5, 7 times 1, 9, which is 5 plus 63, 68. 5, 7 times 2 minus 1, which is 10 minus 7, 3. Then I would get negative 3, 0 times 1, 9, which is negative 3 plus 0. And negative 3 times 2 is negative 6 plus 0, 6. So what I would get is this answer, the answer to the product of AB. But if I switch the order, that would put matrix B first and matrix A second. And it should be pretty obvious why it doesn't necessarily give us the same thing, because I'm using a completely different set of numbers when I'm doing the multiplying. Here I'm multiplying 1, 2 into 5 minus 3. Those aren't the same set of numbers as before. So of course it's probably different, but that would give me 5 minus 6, which is negative 1. Then I would continue first row into second column, which would be 1 times 7 plus 0 is 7. Then second row into first column would be 9 times 5 is 45 minus the double negative 3 is plus 3. So 45 plus 3 is 48. And then 9 negative 1 into 7 comma 0, which is 63 plus 0, 63. So again, assuming I did not mess any of those calculations up, what I would get is this, which again is the product of b times a. So what's important to note is b times a does not equal a times b. Hence, matrix multiplication is not commutative, even when the dimensions are in agreement, like with square matrices. So also, in order to wrap up this section, move into the next section. What are ways that we use matrices in the real world? And I've already presented a few examples, like with geometry, but I've just put in a few bulleted points about areas of math that I could think of where I've seen matrices being used. Digital imaging, like as you could see with taking a shape, trying to recreate a shape in the computer world, change its sides, rotate it, move it around. Always very important. Computer programming in general, a lot of computer codes are written in binary or in languages which value the use of matrices as a way of collecting a lot of data in particular forms. But also in the field of engineering and physics, mathematics, matrices are just used all sorts of different places in the realm of mathematics. And again, why are they used typically? It's to convey a lot of data. It's to represent a lot of different things going on at the same time. And in another very interesting area that matrices are used is what's referred to as algebraic coding theory, a class that I took when I was in grad school. But essentially, a lot of communications, like for example, say a satellite was transmitting data back to us about a photograph that it took of Mars or whatever. And a lot of times data is transmitted in the form of matrices. So say, for example, we take a matrix of data, and this matrix could represent a photograph where each number was coded to being a particular pixel. Or for example, a block of numbers could be correlated to a specific hexadecimal code for an image. And then we could have thousands and thousands of pixels. And if we put together all of those pixels it could formulate a picture. And basically, this long communication, which would just be a humongous matrix of numbers, we could then decode that and figure out, okay, what does this picture actually look like? But one thing about transmission of data across long distances, like from, say, for example, to a satellite or to a spaceship, is that it's not necessarily going to have, the data we get is not necessarily going to be perfect. There's a chance that some of those elements of those matrices got interfered with or are inaccurate. And there's actually mathematical code that you can run to correct errors. Like they can identify an error in a particular matrix, kind of fix the error if it's run through that particular code. And this is all assuming a particular type of data that you're seeing. And anyways, not to get too technical into all that information, but that's what's referred to as algebraic coding theory. It's just another branch where matrices are used very, very used a lot. And really, it's just because of the enormous amount of data. And matrix mathematics is key into that. But in the next video, we're going to transition into systems of equations and why matrices are useful to solving those. So say, for example, we have equations that, the ones we were solving in 3.4 and 3.6, like x plus y is equal to 14 and 2x minus 5y equals 7. But one of the things about those is the reason that those can be represented in a matrix form is because those equations have a very similar setup. And if we look at the following matrix equation and see what happens as we multiply it through, you'll see kind of how a matrix can, how this can kind of help us represent a system of equations. So if we were to apply the rules of matrix multiplication to this particular matrix multiplication this matrix equation within the packet, what we would do is we would take, well, the first row, and noticing that this matrix here only has one column, but it is a match in dimension. It's 3 columns into 3 rows. So this will actually work. And if I think about, well, what does that inner product look like? What I would get is, well, 1 times x minus 1 times y plus 3 times z. And then that would make the first element in my answer matrix, which in this equation is equal to 4. So if I'm kind of reading this equation, what this matrix equation is stating is, well, those coefficients multiply into those variables to produce 4. And then if I look into the second line of this matrix, it would go, well, second row into first column, which would give me 1 times x plus 2 times y minus 2 times z is equal to 10, because that product would produce the second row of the answer. And then the third row would multiply into the first column, 3x minus y plus 5z, and that would make the third answer 14. But what you can see is really this matrix equation is just an alternative representation for this larger system of equations. And the value of matrices here is this is actually a singular equation. Instead of thinking about this as 3 separate equations, we could think of this as one larger matrix equation. And there's actually simpler ways of solving these equations other than the processes we discussed. So in the next couple chapters, we're only going to get into 6.4 and no further, but they go into ways of solving systems like this in an easier ways. So basically, we can use matrix mathematics to try and figure out, well, what's the answer to a system, and make the process of solving such systems easier and more programmatic. And we'll also talk about how you could solve such systems with your calculator using its matrix features.